All right. Well, it's a real pleasure to be here. I really enjoyed that keynote from Kate Gregory and Mike, and just want to thank the organizers of CppNorth for having me, and thank all of you for attending this talk here. So my name is Mike. I'll introduce myself a little bit more in a few moments, but you're here to learn about plugin architecture for supporting extensible software. So we'll try to figure out what that means, how we get to this idea of having software that's extended, and have a lot of fun here. And this can be an interactive talk, so feel free if you have a question to raise your hand. I'll do my best to repeat the question into the microphone as well. And let's have some fun as we start off this conference. So again, this is going to be sort of a introductory software architecture talk, maybe intermediary with some of the things we're going to talk about. We're going to touch on a few different areas of systems and software engineering, and again, try to learn from each other. And you can say that this advice sort of applies once your code starts getting into that zone of, say, 50,000 lines of code, maybe 100,000 lines of code, maybe more. You know, for these, if you have a small hobby project that's a few thousand lines of code, you know, you always got to kind of adjust your advice a little bit. Software engineering is very much about trade-offs in how we design systems. So again, I'm just trying to set the expectations. And my explicit goal today is, again, to introduce to you this idea of plugin architectures and how they might be useful. So let's go ahead and get into it. Any code, and I have written some code that I'll show on the slides, will be available. You can get to it from my website. I'll have these slides up shortly as well on my website right after this talk. And if there's any live coding that I do in the future, you can find out about it on YouTube. Of course, here's why you're here, so you read the abstract. Here's me. I'll be joining Yale University, so I primarily teach. I do other contracting stuff, and I've primarily worked in the game and graphics industry these days. So that's been a lot of fun for me. And that's where you're going to see the examples motivated from this talk. Again, just knowing sort of the domain where I think this software engineering applies, but again, maybe it's going to be useful in your domain as well. And for fun, I like to do a lot of things like travel to great places, like here in Toronto, do video games, cooking, all those sorts of things, so feel free to talk to me about. And we are, in fact, going to talk a little bit about video games, so something that's fun, or even if you don't care too much about video games, hopefully you'll find them as an interesting enough example that we can dive into. So the neat part of software, when I think about it, really is right in front of us. This word right in front of us, software. And that is the soft part of software here, which I think is really cool. And for context in the background, does anybody know who that is? You can shout it out. Yeah, there's a little cheat sheet down here, yeah. Dr. Admiral Grace Hopper, very good. And of course, the Admiral there is working on some hardware, and there's a famous story about bugs and so on. But when I think about this word software and hardware, I remember learning about this in university when I was a student. Of course, now that I teach at university, I have to remind myself and others of this, but the actual origins of these words, software and hardware, have meaning to them. So I was most recently reminded when I was watching a talk from my friend and colleague Klaus, who does a lot of wonderful talks. And he basically reminded us that hardware, again, it has the word hard in front of it as the prefix, means it's not readily changeable software. Versus soft, which has soft is supposed to be sort of malleable or changeable, so easy to modify. And again, if we go back and think about these types of computers, which were mostly hardware, and you literally had to plug in different components to program them, in that time, that was harder to change. So eventually, we worked really hard and got ourselves to develop software, the abstractions that we have as software engineers today, so we can change software. So the software itself, again, the neat thing is it's really easy to modify. So that means we could change our code over time, we could add or remove features, we can improve our algorithms, improve performance, as we develop and iterate in the software development lifecycle. And it's easier to fix bugs as they're deployed to products in case we make any mistakes. Now I think, it's coming here, careful relative to hardware. Because software is very easy to modify, very malleable, and easy to change, we can also add breaking changes, features that might have to be removed that were wrong, bugs, and other types of regressions, right? You can find many examples of this. So we have to kind of think a little bit careful. It's back to the old quote, with great power comes great responsibility, or one must have great responsibility, with this ease in which we can change our software. So what we're going to start working on today, or thinking about, is this idea that I sort of want to think about ways, or a way in architecture, that I can design software to have this sort of solid and stable core. In a way, that core is like hardware. It's going to be protected in a way, well designed, and then I can kind of plug in components to it or extend my software and get the benefits of software, that nice malleability or ability to change. And this leads our software to be open for extension. So we want to develop software with a solid and stable core, again, sort of like hardware, which again has to work. It has to appropriately work. And then we want to maintain the flexibility and ease that we get with our software so that we can extend it, add features, and improve things over time. And just to be clear here, it's a very wonderful thing that we can modify software. I'm not saying, it's very bad or we change things in some way. But again, just thinking about this from an architecture standpoint about how we design a system, I think it's very important and useful to think about how we design for change over time. All right, so just rewinding a little bit for a typical software cycle and thinking about this a little bit. Here's a typical software engineering flow. We edit our code, we compile the code, and then we execute the code. Okay, and of course we're saving in between. And between all these steps, of course, too, hopefully we're doing the other software engineering bits, right? Thinking a little bit, planning, talking with our teammates, making our best efforts, reading other code and examples that we can learn from, using source control, and so on, right? So all in between these steps as we're remembering to edit, modify, and change our code. So what are the challenges here? Because this process that we're doing day by day is relatively simple, right? We edit, compile, execute. Of course, again, that's going to vary depending on the domain you work in. So here are some of the challenges, and especially at scale, as our programs get larger and larger. So that first edit step could actually be quite big, especially if you're working in a monolithic code base where you're compiling maybe other people's projects to get yours to work. Or again, maybe you just have a really big code base. Again, I'm thinking 100,000 lines, million lines of code. Again, we're talking about games today as examples, but maybe in your domains you can think of others, but it's not uncommon to have a game be 2 million lines of code and take an hour or so to build on a fast machine. And with those million lines of code, or even 100,000, you've got lots to understand, or at least your little part in the world of that code base, other developers to coordinate with, some teammates. And I bet if I took a hand, you don't have to raise your hand, but there probably are pieces of code in that code base that you're scared of. They're very brittle. You're saying, the engineer who used to work on that, he left, and we don't touch that, or he left, or whatever. So, this sort of bit rotting thing that can happen in these big code bases. The compilation step, that as well can be quite large. Again, maybe it takes, as I mentioned, a long time to compile our code. There's lots of templates, code that's being generated. There's compile time execution going on now in languages like C++. So that's going to increase this step. Again, not uncommon in some projects I've worked on to take an hour or 2 hours to build. And of course, it can be tricky to deploy that new code. So again, this execute step might be hard to get to, whether that's just figuring out how to get some tests to run on your new feature that you've actually developed. Maybe your environment is being deployed to the cloud somewhere, so there's additional infrastructure and steps and machines or virtual machines to set up. Again, so there can be a lot of different things in our infrastructure these days that make this edit, compile, execute cycle just a little bit more interesting, shall we say. So some software challenges that we have to deal with. We've got huge code bases that might be hard to understand for someone new or that's been working on the project for a long time. Potentially huge compile times for really large projects. And if you're deploying to an already running system, that can additionally have some challenges. When do you turn that system off? Can you turn that system off while you're redeploying new code? So thinking about our goals, and I'm going to keep reminding you of these goals just to keep us on track, but we want to develop software with a solid and stable core, again, thinking of it like hardware, something that we can't just necessarily take out as easy, but we still want new features, improvements to our software. So we want to maintain flexibility and the ease at which we can extend our software. So let's get a little bit inspired and see what happens when we achieve these two goals, just for a little bit of motivation on why you might care about this, or if you're starting a new project and you have that rare opportunity to say, this is how we're going to design something, let's think about what some of the outcomes could be. And I've got to use video games as, again, a sort of motivation, because again, well, that's what I care about and I think they're fun. So let me give you a little brief history of the mod. And maybe this one I'll take a show of hands. How many folks have played or heard about a game called Doom in the 90s? Yeah, most of the audience here. Kind of took over the world. I was, let's see, a few years old, but playing on my dad's lap at the time. That's how, crazy it got, I guess, in popularity. But games like Doom, Wolfenstein, and this is one of the creators, John Romero, reflecting on this game here, were very popular in the 90s because not only was the game at that time the best graphics available and fun and all these things, but it also had the ability to be extended or modified. So people started finding the files that you could change the art assets and create something new. Just out of curiosity, did anybody make a modification or toy around with Doom? I see a few hands going up. Yeah, I suspect this is how some of us got into computer science, messing around with other programs, maybe in ways we should or shouldn't have. So anyways, this idea of modding or being able to take an existing system that's running and modify its components became very popular in the gaming culture. So again, whether that was the art assets or just the actual gameplay or the logic. Now the actual stuff to deal with input-output or graphics or networking or some of these other resources, those were sort of baked into the infrastructure of the game framework, or what we call the game engine. So you didn't have to touch those components, and in a way it made game programming very accessible for lots of folks. So we just had to figure out how to modify and package up new data or scripts with the game. Through the 90s and 2000s, and this is when I was getting started in computer science, you'd buy a game, and on the back of the box, you would say, oh, you can modify the tools and build your own games even if you bought this one. So, here's just a few of the different projects or games that I was buying at the time and also modifying. So we sort of had this boom in the 90s to early 2000s. But I shouldn't say boom because, well, that's still continuing on today. People are still modifying, creating, and using these tools that game developers provide to their customers. Here's just an example here with a game called Elder Scrolls Skyrim. It was released in 2011, and within 5 years, there were 40,000 mods listed in their database. You say, wow, that's how many thousand per year? About 8,000 per year, roughly. And then you get to 2024, where we are now today, and there's 70,000. So people are still building things with these same tools, which is very, very exciting. And all sorts of people. So you can even, later after this talk, not during, you can listen to this, how a lawyer sacrificed their career to redevelop a Skyrim mod. And they made a career change by doing that, by doing something that they loved. So, the longevity of such of these projects from, a really strong infrastructure, the Skyrim game engine or Wolfenstein game engine or Doom, really is impressive and kind of inspiring if we can think about how can we do that for our projects. So why allow your software to be extended and consider allowing users to modify or extend your data in some way Well, there's a software reuse case, both for you, if you're going to develop sequels for these products, or for your users, as demonstrated in the modding community. In fact, there's many, many stories about, again, people, myself included, getting their start in game programming and going off to develop actual games because of these mods. You can also enable others to do work in your systems. So this example here on the top right here is a visual scripting language that's built on top of Epic Games' Unreal Engine. So this visual scripting allows folks who are programmers, they're technical, but maybe they're not diving into the bits of the really low-level stuff, and they want to focus on gameplay programming or prototype an idea really quickly, or maybe they are just artists. So you have that advantage of being able to open up your system or your ecosystem to others. There's obviously the economic benefits if you're able to build an extensible system. The licensing that you can get from your tool or product, this is the famous thing from the game engines, or it can be other things like markets that are created for extensions that can be sold in plugins. And then the second point, of course, is just the good karma that comes from this. Because as those mods or modifications and extensions get released for your games, well, that builds community. And again, it's in that same infrastructure that you have. So again, from a economic standpoint, it should be a win-win. You've got folks making great content, learning stuff, maybe building products themselves, and then they're doing that in your ecosystem. Now, why not allow your platform to be extended, right? This is a software engineering talk, so there are trade-offs always here. You have to be careful with what you're exposing for folks to have access to. Are you giving them everything? Is it totally open source, or is it just going to be a piece of it? Do you want to give that proprietary encryption algorithm that you have that keeps our data safe as part of your API? Again, you got to kind of think about those things and think about how you're going to release your software in that case. So you do have to think about those sort of boundaries as far as public and private, your implementation details, and so on. And we're going to have some talks at CppNorth about that. And you also have to think about some other stuff that could happen once you start opening your system, like if you're going to have a scripting language, and that's what your hook is to build your extensible software. Once programming languages start talking across boundaries, you got to figure out, well, who owns the memory, or how are you going to manage that? And third here, once you have that critical mass of users, so maybe 70,000 mods or people relying on your software, you kind of have to be careful about how you change your APIs. So you have to plan for that. Having stability, when are you going to break things? How are you going to version things so your developers know how they're working in your ecosystem? You now need to support a lot of features and maybe many versions of your software. For those who haven't heard Hiram's law, Hiram Wright out of Google, he has this nice law that says, with a sufficient number of users of an API, it does not matter what you promise in the contract, all observable behaviors of your system will be depended on by somebody. Well, I guess where we left off was Hiram's law, so let me give a few anecdotes. So with a sufficient number of users of your API, right, somebody is going to depend on some functionality. What are folks' thoughts about how you can sort of combat this? I don't know, they could be C++ things. How do you make your API a little bit more resilient to change? Has anybody learned any sort of interesting idioms or tricks? Expose interfaces and not concrete implementations. Yeah. So, error check all your inputs. Yeah. Other thoughts?
Make the API intuitive.
Make the API intuitive. Yeah, so that counts for names, maybe how you're passing in data. Again, with the interfaces, passing things maybe like structs instead of a million different parameters, right, can provide some resilience. And then, of course, sanitizing your input. That's going to become important later as we get back into plugins and say, what happens if, well, we crash something from some external party? Was there another hand?
Yeah, I think Microsoft's COM going for example, like interface versioning and query interface. Another vendor
Microsoft's COM. So, I caught a few things here. So, versioning, of course, having some sort of information about what components that you're loading, because you have to be able to check. Also very important for plugins, yeah, and ABI resilience. There's other little things. Do folks know the pimple idiom? Pointer to implementation. That can sometimes be handy. Again, the address of a pointer is usually a little bit more stable than the size of your struct. So if you're relying on sizes and these types of things. So these are kind of, well, that's kind of nice. We can talk about some of this because I don't have specific those details in here. But they're all important things to think about for building a resilient API. So that's Hiram's law. Other questions or thoughts? Yeah.
No, also, don't implement an API until somebody asks for it.
Yeah, don't implement an API until someone asks for it. Yeah, don't go on a feature sort of crusade and building things. Yeah, I sort of say, and the other thing with building the API and thinking about the actual inputs, you can always mock those inputs and so on. So if you get your interface right and spend a lot of time doing that, it usually leads to a better, experience long term. Let's see what else we got here. What do folks think about live patching code for modifying it? You've got a system that's running, and you've got to inject some code into it. Hot patching, monkey patching, or live patching, I've heard these terms. Any folks with experience in this? How's that for a system? Yeah, I see some hands going up. Yeah, it can be tricky, can be useful. In games and game engines, we use it sometimes for a hot reload, so you don't have to slow down your development cycle. So again, those will be a few things to think about. So I'll remind us of our goals. Perfect intermission there. Okay, so we've been looking at games, talking a little bit with the folks here about plugin systems and some of the different techniques that you've been using and about good software design, right? Some of these things like building our APIs. So let's think about developing software, again, with a solid and stable core and to maintain flexibility and ease of extensibility. All right, first goal, how do we modify software? Here's the three different tricks, right? We can just edit the code. We can edit the source code with discipline because we're trusted. And then, of course, we could do things like live patching, which I brought up briefly and, inject code into a running process or do some instrumentation. Okay, so just take a moment, think about these three strategies. Keep these in mind for a few moments here. And think to yourself, do these strategies help us meet this goal of building, software with a solid core? If we just, for instance, just edit the code. Well, again, we always have this option. We can always rebuild, restart, and kind of go from here. But again, you got to kind of think about this for those 70,000, hobbyists or professionals who are modifying a game and saying, here's a million-line code game engine, just go modify it however you want. That's maybe not a great experience, and you sort of don't know which pieces to touch here. So let's think a little bit more about this. And let's try to approach this with some discipline. So maybe we can use some programming language feature, like inheritance. We can override some behaviors, maybe add some constraints or concepts, C++ things here. And that's a little bit better, right? We're following some design pattern to do this. Maybe something like an open-close principle with a visitor pattern. Again, that can be acceptable, right, for extending our software. And we sort of have to build a core, because you have to come up with this abstraction or these interfaces when you develop your code. And then, of course, there's another strategy for just live patching. Just compile some code, take a system that's already running. And this is going to depend on your requirements. But it's a little bit more risky. It just depends on what domain you're working in if this is the right path to go. meaning that you might have some constraints, some permission levels, things to do with interfacing with a process, a live running process. And there's frameworks for this, like Intel's PIN framework that might be of interest. But this probably isn't what you want to give to your users and say, just modify the running application and then it'll magically all sort of glue together and you can distribute that. These sort of strategies of just modify the source code and here's a huge code base, maybe they're fine. Again, we can sort of argue this in different ways in different domains. But you really do need sort of good discipline. You need to do things like write tests. You need to sanitize your input and really use your programming tools, again, judiciously, like constraints and contracts when we get them and so on. So let's say if we can sort of focus more on the extensible system side here, just controlling the bits where new code enters. And let's talk about this, sort of maintaining our flexibility and ease at which we extend our software. So here were a few ideas that I came up with. And these were pretty magical to me when I first started thinking about these when I was learning programming. So things like configuration files. Oh, you can pass in new data and change how the program's behaving. Right? These are the sort of first things that you mess around with when you have a mod and you kind of change some values and all of a sudden your character's 10 feet taller than they should be or something strange. But it's kind of cool and it's data driven and you really didn't have to do that much work, right? Just changing a text file, for instance. But then there's other more powerful things that you can do, like create a command-driven language or interpreters or scripting languages, as someone mentioned earlier in the audience. And then ultimately kind of land on maybe plugin systems and see if we can get the best of all these worlds here. So, exploring these ideas just a little bit, and again, thinking to yourself, do these strategies meet your goal, okay, for whatever system that you're trying to build? And each one sort of increasing in power as we go. So the first idea with configuration files is this idea, again, that you can effectively read in from maybe the command line arguments, or at some point in your program, just literally open up a file and start reading in text or binary data. In games, this is going to be your art assets are almost always loaded like this. They might be baked into the executable sometimes, but usually they're loaded up in some sort of package. Other things like rules or settings are often read like this. And you can even create different types of data types by using configuration files. So there's something called a type object pattern where you can use to sort of set attributes of a class or fill in and set things up here. So I can explore that later if you want to get more in depth with configuration files. But for any of these sort of data-driven styles, one thing to consider in your application too is, is your system going to be loaded up or configured at the actual compile time, or is it at runtime? And if it's at runtime, is it at, when the program first starts? Is it at any intermediate point where it could load in some new data? And that's going to inform your sort of resilience strategy, how you sanitize the input, how you crash if there's an error, whether a restart's acceptable or not. So those are just a few things to think about when you're loading your data. So we can add some more power to this and say, okay, now text files, they're not just little configuration scripts, but they're actually going to do stuff. They're going to have commands. So you can sort of add more power to your text files by making them what I'd call a command-driven language. So somewhere between a domain-specific language, but not quite something that needs functions and if loops and jumps, right? It doesn't have to be Turing complete necessarily. But something like this, where maybe you have a script or a series of commands, right? Showing an image, loading some data, fading the music out, and then playing some music, almost like this PowerPoint presentation, auto running as you click and some event happens at some moment. So again, this could be another way to make your application more data-driven, and you could imagine in a gaming scene a cinematic sequence that's set up like this, loading some data, showing something, and then moving to the next scene. So, I mean, at that point, if you have something where you have commands, you might as well get all the power, or consider getting all the power here with a script language. So you can embed something like Python, Lua. I mean, there's a ton of different languages and use cases here that you could use. But then you get the whole power of that language and that ecosystem of that language as well. So just as a brief intermission, if you do want to do something like this or explore something like this, I have many examples on PyBind 11, but where you could take something like this class that's generically just called a component, and you could wrap it using something like PyBind 11 or Boost Python, choose your favorite framework, and then have this class and its member functions available or exposed in a Python plugin. So on the top right, I just have a brief example of importing that library that's been wrapped, and then using that component and setting some data for whatever that type is. And you can even go further, and then you can embed an actual Python interpreter into your C++ program, and then you can have your users use Python and run your code within the Python interpreter in your C++ program. So if you'd like to see those types of things, that's what the link on the bottom will be available for. So that gives you a lot of power. Now, of course, you've got to think a little bit about ownership things, where memory and resources are going to be allocated, and so on. But again, we're getting something quite powerful here. But at this point, that sort of brings me to idea number 4 here, which is just to say, let's just have a plugin system. Let's actually compile code into shared libraries and just get the speed of the compiled system in the language that we're already writing in and use that to build extensible software. So the way that this works is, again, you're just going to compile regular C++ code as a shared object, a DLL, a dilib, depending on whatever your platform is, and be able to just work through your native language and create basically a C function so that you can communicate back and forth with it. And this is also going to allow us to have this sort of plug-in system. Okay, so thinking to ourselves, does this strategy work here? With all these sort of data-driven options here for building our software. Well, having our application being data-driven in the first place sort of informs how the core of this system is set up here. So I'd argue that this naturally tells us that we need to sort of center APIs that might be around this idea of being able to be plugged into. So this plugin system seems like a really neat or a good idea if we're going to have a large project with lots of code and we want to be able to extend it in potentially unpredictable ways, right? We have 70,000 users modifying some game framework in ways that we can't expect, or maybe we have some tool where we can't really predict what artists are going to do with it. So again, we want it to be wildly open for extension in this way. But we still want control of our core system, like a game actually running, processing graphics, and so on. A question, yeah.
I'm wondering, is there a bright line between options 3 and 4? Like, is there something about number 4 where using shared libraries makes something plugins, whereas running scripts does not? I ask because I'm thinking in particular about browser plugins. Browser plugins tend to be basically pieces of JavaScript code, which from the point of view of the browser as a native application are basically just scripts the browser executes. But we think of them as plugins, so I'm wondering, is there a line there, basically?
Yeah, so the question about between ideas 3, plugin systems, and scripting, I don't want to draw a hard line and say, one of these is better than the other. And in fact, it's a good idea to know that we can, in fact, combine all these, right? So my system might actually start here with a configuration file, and then it does a series of steps here. And in fact, one of the tools that we're going to look at towards the end, Maya 3D, it has scripting and a plugin system. Because you might want 2 options. One, to be able to just write scripts and sort of load those as plugins, or to actually be able to load native code and execute that. And you might want that plugin to actually be able to run scripts as well to do interesting things. So you can combine these again in as wild of ways as you like. Other questions at this point? Or challenges or trade-offs? Yeah.
I guess one of the main trade-offs being that with the real plugins, you can have the full performance of, one of the trade-offs being with the full plugins, you can have the full performance of your system, whereas with the scripting language, you're going to be somewhat limited.
Yeah, so the question about trade-off with performance. So generally speaking, I would say, I can probably safely say at this conference, right, we're probably going to get the best performance from C++ if we use a C++ plugin. Now, we have to be a little bit careful because I'm using examples in, say, Python that I'm going to embed, but there might be, we could embed C# like some game engines have done, or Java, and those have interesting sort of just-in-time compilation things. So again, this world starts to get very interesting very quickly. So I'll be careful with performance. And there's also the other question, which I have sort of at the end, pre-cooked Q&A questions, if no one asks, but about do we have to dynamically load it, or, is that bad? Why don't we just statically compile everything in? What's the sort of performance implication? So we can think about those things as well with our plugin system. Yeah, great. Other questions? All right, we're doing good. All right. So kind of arriving to this solution, or this way of thinking about data-driven architectures gets us to a plugin architecture. Again, this idea that we can have shared libraries that we're loading that help us with our challenges, right? Because we want this big, maybe performant code base, but the code base was too hard to understand because everything was in it. It had huge compile times, and we already had maybe had a system that's already running. But again, the problem that the plugins solve for us is we're able to load shared libraries while our system is running. It's open for extension, and we kind of isolate our code that we have to modify to just that plugin. Okay, so here's what it looks like, a plugin architecture. Right? The main thing that I'll focus on is we need some sort of plugin manager that's going to handle loading these external plugins. Okay, and then your core API still has the systems, again, if you want to think about this in a gaming context, for handling sound and graphics and networking and specific APIs and so on. And we might have to think a little bit about what APIs we expose to our plugins, which sort of interfaces and behaviors folks can override. But that's the basic idea. Plugin manager loads plugins, inserts them into some system, and it runs. Every iteration of the loop, or within some event that happens, perhaps if somebody clicks something or whatever. And getting back to the very start of this talk, the way I'm thinking about this, or I'm sort of developing my ideas about this, is I want our core API again to be more firm, for us to think about it a little bit more like hardware. So we want it to be a little bit more resilient to change. We want to design it that way so it's resilient for change. But our plugins we can kind of go wild with. We can prototype, we can try different functionality. Again, that's what your developers or your community is going to do. So again, we almost want to think about the core API as a black box. Now, of course, the folks working on your actual team on the core, they have access to the source, right? So there's sort of two parties here. But to the outside world, right, you develop plugins to plug into a system that just runs. All right. Okay, so if you're curious about how to actually do this stuff, to look at a little bit of code here, the basic mechanism that we need is the ability to load a shared library. Now, again, I'm usually a Linux person, so these facilities are DL open, dynamic library open, and DL sim for looking at the symbols of that opened library file, or that object file. So that's a typical way to do this. So as just a brief example, at line 14, you don't have to read it, but basically I'm just loading up a math library. You can load it up lazily, so as it's found here. And then if we come down, assuming we found the right library, at line 26, I'm finding a particular function, cosine, okay, or whatever function that you've exposed, and then we have a pointer, a function pointer to that function, okay? Now, somewhere we do need to figure out, okay, what types of names of things are in my actual plugin that the user wrote. So they do have to sort of register or export out those names. Maybe they're in a text file, or maybe they're managed otherwise by your plugin system. And we'll show that in some next slides here. Okay, so we've got our plugin system. We're going to have some plugin manager, some way to add in plugins here, and sort of localize our complexity to, per plugin that's doing a specific role, and then our core APIs. Okay. And again, hopefully this is going to help us with our challenges of avoiding recompiling the whole code base, understanding the whole code base, that we still have to understand our specific systems that the plugins interacting with. And then of course you have your core team on the other side that understands their portion, but that's the idea. Okay, so here's what a plugin manager could look like, some actual code here. To basically handle the loading and unloading of different libraries. So this is usually going to be some interface built on top of DLOpen, DLSim, if you're at Windows, git procredus and load library, these types of functions. And again, you might also think about when the plugin manager runs. Is it at any arbitrary point? Is it just at the start of your program? Again, just depends on how you want to implement this system. This is probably one of the use cases I can think of the very controversial singleton pattern. So again, I'm just going to throw that out there just to see if we get any, if folks have thoughts on that. But I've found it, a single entry point for managing your plugins may be useful. It may also, you need to think about how you're going to test these things, though, which is sort of the anti-part of singleton. Now, as far as building your actual plugin, you're going to have some interface for your system here. Okay, so this might be, well, based off the function names, update and render. Maybe this is drawing something in graphics. So per system that you want to expose, you're going to have some sort of interface for that type of plugin that you want to actually write. So maybe for your graphics, if you want to expose that, your sound, your networking, whatever it might be. Again, you can have different interfaces into those components. And again, that's the way to just expose the actual functionality that you want or that you're comfortable for folks to plug into. So here's an example of building a custom plugin. So this would be in its own separate C++ file, my custom plugin, and you're going to inherit from that interface. So that's what this example is demonstrating, and then overriding each of your functions. Now, in order for our plugin to actually be sort of discoverable, we do need, again, to load in those symbols. So a typical pattern that you're going to see here is to have some basically factories here, or a way to create an instance of my custom plugin. So that's what's demonstrated between lines 41 and 43. Just a function that returns my custom plugin here. And again, usually we make these C-based, again, to make it a little bit easier. There's no mangling to deal with, and you can talk to any C-based language where there's that foreign function interface. And then, of course, you need a way to delete your plugin as well. And at the very bottom, there's usually some, again, plugin registry for how to refer to your plugin, and that might also be where you expose the symbols as well. All right. Questions about any of this so far? Right. Otherwise, I'm going to show a few case studies here, a few real-world systems, starting with Maya. So Maya, if you're not familiar with, it's a 3D tool by Autodesk. It's had a long history in graphics with, I believe, some origins here in Toronto, if I'm not mistaken, from their previous company. But just looking at this interface, you can tell it's kind of ripe for doing plugins, right? There's all these little buttons that you can click on, and every little button probably does something different, right, to the actual 3D object here. And we're actually going to find out there are lots and lots and lots of plugins here. Now, to the earlier question, Maya is actually an example of a tool that's been extended by plugins. There's configurations, and there's not one, but two scripting languages, Mel and Python in Maya. Maybe more that I don't know about, but at least two. All right, so what's a plugin look like? Well, we can look at, or we can zoom in later onto it, but if I just want to highlight the common parts here, that basically this top box here is just some new class, and it's inheriting from some interface that's been exposed. And we've got a few functions to override. And this function is just labeled do it, for whatever that means on a button click. Just do the action, whatever is executed in this function. Okay, so same pattern we saw before. Just override, or excuse me, inherit from a base class. And then what's at the bottom? There's a way to create our plugin, and a way to initialize it, and a way to uninitialize the plugin. Or sorry, there's a way to create the object that's here, and then we want to initialize or deinitialize the plugin. So that's just registering it and saying we now have this new class, hello world, that can do the do it member function. Okay? Now, something we haven't also talked too much about is with these plugins is how we're going to handle errors. So just highlighting, immediately what I see in the and have used in the Maya SDK is, well, it returns error codes. And the error codes are basically using the same interface. They return an mStatus object that the core API uses, so it can understand, when this plugin's been used and running, if some sort of error state has occurred here. So that's also important to be able to retrieve errors from your plugins and decide what you want to do. And again, this could range from crashing your system to maybe not the best idea, to logging the errors, deinitializing the plugin. So again, you'll have to decide how to handle that. In most cases, in the Maya plugins that I've built, the error is it either doesn't load or the function doesn't execute. It doesn't call the actual do it function if it doesn't get a success message back. So Maya itself as a tool is filled with lots and lots and lots of plugins. In fact, if you click on this list that's linked here, you'll see just a huge list. It wouldn't fit in a slide for different things. And within the actual Maya tool, from the toolbar, there's a ton of different plugins that you can see that are loaded. Some of them are auto-loaded, and you can control, again, at startup if they are auto-loaded or not. All right, so moving towards the end here to Unreal Engine, another example here. And you're actually going to see pretty much the same pattern here once you sort of understand this plugin pattern here, which I thought was really interesting. So going from a 3D art tool to a 3D graphics engine. But what's sort of interesting here is, again, they have the different modules that you can plug into. And they have a lot of different graphical user interface components for selecting which exact component that you're going to override or which functionality. So I thought that was really nice. But if we look at the code, we're going to find basically the same thing here. So, again, there's going to be some sort of startup or shutdown module or plugin, however you want to call it, and then at line 20 is just demonstrating the plugin button was clicked. So same idea here. And again, typically with these plugins in both tools, there's going to be some sort of metadata associated with these. So what's the version, what's the name, when was it updated, this sorts of information that's going to be useful to understanding, does it connect back to the core API? So was there a version mismatch, for instance? And this is, again, helpful for the users for any reporting. All right, and the last tool I'll briefly talk about before we summarize here is a tool that I've used, Qt Modeler. And this one's just a pure C library, which was a little bit interesting to look at. And effectively, the way that they left their tool open for extension was to just give you a header file with a list of functions in it, and then you download a new version of their binary executable, and then you have those functions exposed. So again, if you're going sort of a pure C route, that can be an option too. So it doesn't have to be super, super complicated, right? You can keep things to just, again, a header file with a binary object. And then you put that binary or that library file in a plugins folder, and that's it. All right, so wrapping up here, and a few more resources. The main thing that I've been thinking about has been sort of developing this talk and working on a relatively large project recently is from this book, The Rules of Programming. And again, it comes out of Chris Zimmerman, who's a game programmer at one of the Sony PlayStation studios, Sucker Punch. But it's this idea that's drilled into my head now about localizing complexity. And I think a plugin system's a pretty good idea. A lot of the design patterns that I think we learn is usually they're trying to drill these ideas in our minds. So I think this is a really just nice text that I would recommend. So today, we've talked about a plugin architecture. We've gone on a little journey here. Hopefully help solve some software engineering problems at scale, at least exposing this idea of how we might design a system or maybe part of our system to be open extension by plugin. And hopefully I've influenced, or as my mind is always changing about software things, but just sort of harden this idea that maybe our core systems we should treat a little bit more like hardware and really focus on the resilience, the ABI stability, and so on, but leave them open for extension for rapid prototyping and being creative. So that's the basic idea there. All right, so I got a bunch of thoughts here, but I'll leave it for Q&A. Things like, what if the plugin's leaking, the plugin's crashing, versioning, do I have to use object-oriented programming? Should I use a plugin or an embedded scripting language, as was mentioned? If you don't like dynamically loaded libraries because it's too slow or something. But I'll leave those there for later. So thanks for your time. Thanks for your patience with this presentation. And I'll take any questions. Yeah, question. Yeah.
Hi, thank you for your talk. What are your thoughts on opening it for extensions through GUIs as well? Like there's oftentimes a lot of scripting, but then users want to see their buttons too. Like, where do you draw the line? Like, do you let the users build their own UIs, or do you wrap around on top of your own UI framework?
Yeah. So a few thoughts on user interface and what you sort of expose. I thought one, the Unreal sort of model is very interesting because they have sort of the different components, in their own user interface for what you can quickly click on and modify. This includes stuff like for their visual language blueprint, where you want things like to just grab whatever the generic button is and expose that. I think that's totally fine. In Maya, they're pretty flexible in which you can actually get a handle into the OpenGL context, and then you can just draw whatever you want. So I sort of like that. Again, I think it probably depends on who you're opening it up for, I guess. I suspect if you just open up a common interface of tools for users, they'll just use that and go that direction. But I don't have any immediate reasons not to use some framework. Now, if somebody's going to download the whole Qt and you're using WX widgets, that's sort of on them if their plugin becomes 100 megabytes or something. Again, limit dependencies is my philosophy. Use what's common. But if there's no reason to close stuff for users, probably don't need to. Unless you've got like security concerns or other reasons something should be sandboxed. Yeah, so I don't know if that gives you a direction or not.
Maybe I'll come talk to you after.
Sure, yeah, please do. Yeah, other questions or thoughts? I'll leave up the random ones I had up here as well. Yeah.
Do you have an example of like open source plugin managers that we can review?
Question about open source plugin managers that we can view. Not that I looked at. I just look at other code bases or tools that I've used and mimic those. Yeah. But happy to follow up. I'll add it to my list. Yeah, yeah, question.
What about thread safety with Spark plugins? Like, how do you even begin?
Yeah, so the question is, what about thread safety? How do we even begin? Yeah. The comment is, don't make it single-threaded, yeah.
So the plugin can never use a single thread.
Well, I think it kind of relates to how I think about memory and resources. So if you're able to expose, like in a game, for instance, they'll have like threads or jobs that they'll call sometimes. So if you're able to expose that in your plugin interface to be able to create and be able to reclaim that resource, then it's probably feasible, but you want to probably try to do it through like the core system API. So that way you know what happens, like if the plugin gets, unloaded, but there's like still a thread running or something, right? You can run into like, it is tricky. I ran into the same stuff with I ended up just, again, I took the easy way out and I was just like single threaded, I'll think of a better algorithm. But there are tools certainly to, and in that Maya space, to multi-thread things, right? You want performance, but probably do it through your core API if you've got control over that. It's probably an interesting experiment to take one of these tools like Maya and Unreal and just throw, I don't know, P threads in there and let them crash and see what happens. And that might give some insight as well to see how resilient, or you can also use your tools like LDD to see what thread library maybe they're linking to and at least try to have some compatibility there. I'll also put this under the generic advice, and I'll flip to the next set of pre-made questions here. For memory allocators, kind of the same rule. It's like you either want to live inside your core API that's giving you memory resources, like mem blocks if you want to call them, or just not to use a different allocator, or it has to just live within that plugin itself only. Yeah, another follow-up?
I actually have kind of a follow-up to that.
Sure.
Because my familiarity is, again, more with scripting-based plugin systems where you have complete control over what you expose to the script. But let's say you do have a native plugin system. Is there some way you can prevent the plugin from just calling malloc? Are there mechanisms for that?
Yeah, so the question...
Or other things it wants to do?
Yeah, so can we sort of sandbox it? We could probably... immediately off the top of my head, I was thinking you could... Before you load a tool, you could probably search the symbols and see if it has malloc as one of the symbols, if it's directly exposing it. That's a good question. I don't have a lot of, this is a great question for security folks and folks who like sandbox stuff. Because the first thing that came to my mind is Godbolt, how they sort of maybe sandbox their stuff. I don't imagine it would be much different. But yeah, I don't have a direct answer. But there must be some way to sandbox these things. Suggestion or yeah?
To follow up for that, you could put it in another process. If you're searching for symbols, you could still use assembly to make syscalls.
Oh, sure, yeah. Yeah, so the comment was to put it in another process, and you could still use assembly to do syscalls, yeah. Yeah.
We've kind of run over at the end of our time period. Mike can meet with you in the hallway afterwards, but don't want you guys to miss out on too much of your lunch and let the other guys eat everything. So thank you very much, Mike.
Yep, thank you. Thanks for hanging around, folks.